So welcome to Reigate College Maths Year 2 Statistics, and the next video in the series on the normal distribution. This time we are looking at using the normal distribution to approximate to a binomial distribution. So binomial distribution that you met in year 1. So you'll have seen this bar chart of binomial probabilities, and you've seen the bell curve of a normal distribution, and you can see that they are approximately the same size, size and shape. The difference here is that we've got probabilities for a binomial distribution of equal to certain values, represented by a bar. But the probabilities for a normal distribution are only within a certain range. So the probability that a normal probability equal to a given value is always 0. So what we can do is we can use the normal distribution to approximate the binomial distribution, but only under certain conditions. And those conditions are, first of all, that n, that's the number of trials in our binomial distribution, has got to be large, and our rule of thumb for that is that it should be at least 50. That's only a rough ruling, and it doesn't mean to say that you really couldn't use it for something slightly smaller. But if you go too small, these overlaps here and these sort of underlaps, I suppose you'd call them, get very big. So we want those really to be small enough that we can ignore them. So n has to be large, and the other thing is that the probability of success in the binomial distribution, p, has got to be close to 0.5. The problem if it's not close to 0.5 is that our binomial distribution becomes skewed away from the center, and a normal distribution is always symmetrical about the center. So long as it's close to 0.5, it'll work reasonably well, but the further away you get, the worse it works. Another point to note about the binomial distribution is that the two parameters for that are n and p. The parameters for the normal distribution are very different. They're the mean and the standard deviation. But we've got a formula that for a binomial distribution, the mean is n times p, and the standard deviation, or the variance, is n times p times 1 minus p. So the variance is the square root of that. So the square root of n times p times 1 minus p. What we have to do very carefully is we have to think about what probabilities we want. So for our binomial probability, which is a discrete probability, if we want the probability that x is equal to 6, representing this bar here, we want the normal probability that x is between x is basically any number that would round to 6. So that's anything greater than 5.5 and less than 6.5. So between those two probabilities. So that will be our continuous probability, our normal probability. And then there are corresponding ones for whether we're going greater than or equal to, less than or equal to. For a discrete probability, it's very important that you distinguish between less than and less than or equal to. But that really doesn't matter for the continuous probability. But it will matter when we look at what normal probability we want. Turning that equals a value into between two values is called the continuity correction, and it's absolutely critical that you get that each time. So let's have a look at question 1 here, which is really asking us about whether it's appropriate to use a normal distribution as an approximation to a binomial distribution. So for each of the following binomial distributions, here we are, we've got x is binomial with number of trials 5 and probability of success 0.5. Is it appropriate to approximate it by a normal distribution? So for A, we're going to say no, can't approximate it. No, because the sample size or the number of trials n is too small. N equals 5 is too small. So it can't be approximated. For B, let's look at this. X is binomial with n equals 500 and p equals 0.5. Well, that matches the conditions that we want. So yes, we can approximate it because n is large and p equals 0.5. So now we've got to say what distribution we're going to approximate it by. Well, we need to work out the mean and the standard deviation of this distribution. So mu is equal to n times p, which is 500 times 0.5, so 250. Sigma squared is equal to n p 1 minus p, so 500 times 0.5 times 0.5, which is 125. So sigma is equal to square root of 125, which is, what is that? Square root of 125 is 11.2. So we can approximate by, so approximate by let's call this distribution y, which is going to be normal with mean 250 and standard deviation 11.2, so 11.2 squared is going to go there. Okay, so let's look at C. C, we're going to say no because P is not close to 0.5, and D, we're going to say yes, N is large and P is close to 0.5. Okay, 0.549 we're going to say is close enough to 0.5. Oh, that's a bit wonky, isn't it? Let's try that. That's better. So again, we're going to work out the mean and the standard deviation. So mu is equal to, what do we have? We have 1000 times 0.49. Mu is equal to 490. Sigma is equal to the square root of 1000 times 0.49 times 0.51, and that's equal to 15.81. So approx by y is this time is normal with mean 490, and then we've got standard deviation 15.81, or we could write this as 249.5. That would be the variance. Let's write this down. Same as N 490 15.81 squared. We could write that in either way there. Okay, let's go and look at question 2. Question 2 I'm actually going to write on the workbook here. So this is all about the continuity correction. So for a binomial probability where x is equal to 9.7, what we want to find is the boundaries for that on the continuous, the normal distribution. So what would round up to 9.7? Well, that would be 9.65 up to 9.75. So we want x greater than 9.65, less than 9.75. X greater than or equal to 9.1 and less than 9.3. So we want things that are going to round to 9.1 included. So that's going to be 9.05 less than x on that end. But up at this end, we don't want to include things that round to 9.3. So we do want to include things that round to 9.2. So we're going to have up to 9.25, but not above 9.25, not 9.26, for example. Next one, we've got whole number values now. So x greater than 8, but less than 12. Well, we don't want to include 8 there, so we're going to go 8.5 at this end is less than x is less than, and this time we do want to include 12, so 12 represents, or is represented by 11.5 to 12.5, so we want to go up to 12.5 this time. This time we are including 8, so we're going to have 7.5 up to 12.5, and this time we're not including either, so it's 8.5 up to 11.5. So that's how we work out the continuity corrections. It's important that we do that. We'll see that I think in question 3. So let's go and have a look now at this question 3. So question 3, students pass the university entrance exam with probability 0.7, and we're taking 100 students picked at random. So for A, find the probability that fewer than half of these students pass the examination. Well, this is asking us about a binomial probability, so we're going to say x is our binomial distribution, B with n equals 100 and p equals 0.47. Half the students pass, fewer than half of the students pass the examination. So x is representing our success here, so we're saying that we want the probability that x is less than 50. Remember that our calculator calculates probabilities which are less than or equal to, so that's the probability that x is less than or equal to 49. And let's go and see that on the calculator. Let's do a little refresher on how we find binomial probabilities. So we're going to go menu, oops, where are we? Here we are. We're going to go menu and distribution, so that's 7, and then we're going to go binomial, and we want cumulative distribution, so we're going to go down to here, so that's 1 now. We're going to just say variable 2, so we've now got x is 49, we've got n is 100, and we've got probability 0.47, and there's our probability of 0.6922. 0.6922. Then the next part of the question says, for B, using a suitable approximation, find the probability that fewer than half of the 100 students pass the exam. So it's asking us about the same probability, but it's asking us to approximate it now by a normal distribution. So we're going to say approximate by, let's call it y, is now normal, and we've got to work out the mean and the standard deviation. So let's just do that. Mu equals np, which is 100 times 0.47, which is 47. So we're going to put the mean in there, 47, and we're going to find the standard deviation. Sigma is equal, let's find the variance, sigma squared is 100 times 0.47 times 0.53, and that comes out to 24.91. Let's just find the standard deviation as well, is square root of 24.91, which is 4.991. So we're going to put in here 24.91. I'm putting the variance in there. Okay, trying to keep this question here so that you can see it. Well, it's not really working. Okay, never mind. Let's get rid of that. Okay, so we're approximating it with this normal distribution here, and we still want the probability that x is less than 50. So that's approximately equal to, we need to translate it into y using a continuity correction. So less than 50 means that we're not including 50. And 50 is represented by 49.5 up to 50.5. So less than that is the probability that y is less than 49.5. We could include less than or less than or equal to here, it wouldn't make any difference. And now what we're going to do is we're going to go and find that normal distribution probability on our calculator. So I'm just going to go, I'm already in the distribution mode, I'm going to say select type, so this is normal cumulative distribution. We've got a lower end of, let's make it minus 1,000, minus 10,000, an upper end of 49.5. We've got sigma was 4.991, and we've got a mean of 47. And we can find that probability, and it comes out to 0.69178. 0.691. Actually, we had it to 4 decimal places here. Let's put it to 4 decimal places here as well. 0.6918. So you can see that these probabilities are pretty close. They're not exactly the same, but it's a pretty good approximation. So question C Using your answers to A and B, calculate the percentage error incurred when using a normal approximation in this case. So percentage error, what we're going to do is we're going to find the difference between these two and then divide by the actual percentage. So percentage error is equal to 0.6922 minus 0.6918. So that's the absolute error divided by the accurate value 0.6922 multiplied by 100 for a percentage. So let's again put that into the calculator. So we're going to go menu, back to calculation mode. Let's put it in as a fraction, 0.6922 minus 0.6918. Down at the bottom, we're going to have 0.6922, and then we're going to multiply by 100 to turn it into a percentage, and we get the percentage error of 0.06% or 0.058%. That's 0.058% percentage. So that's an example of approximating a binomial distribution by a normal distribution, and also finding the error between them and the percentage error. And that's the end of this video on the normal approximation.